Hello again. Now in this video we'll move into section 11. We're still factoring, but now we'll finish our factoring techniques with some special forms. All of our special forms are going to be binomials. So we've already gone through quite a bit. We've seen how GCF, greatest common factor, applies to any situation, 2-term, 3-term, 4-term. We can always look for GCF. Then we saw 4-term polynomials. Grouping is our main technique that we would use. We then went through a whole section on trinomials. We saw that sometimes there is multiple steps, but still our trinomials, we had our grouping number technique. And now finally some special forms, some binomials. The first one that they introduce in our book is what they call the difference of squares. And they jump right in with a very nice formula and explanation. And what they show us is that a squared minus b squared can be factored into quantity a minus b times the quantity a plus b. I actually think in our book they do this the other way. But again, our order of factors do not matter. But what this is actually saying, it's a very, very specific special form. A binomial where each term is a perfect square. If you have that situation, it still factors into these two nice binomials, because if I multiply this out, even as a generic formula, a times a is a squared, a times b is ab, minus b times a, well, I'll just change the order, but I still get a minus, and instead of ba, I'll write it as ab, and minus b times b is minus b squared. If you have this special circumstance, if you get this factoring, the reason it works is because that middle term, if you try to multiply it out, would always cancel, so you're just left with the a squared minus b squared. So that's why it works. That's why it's not just a trinomial that goes to two binomials. If it's this very, very specific binomial, it'll work like this. But this is where we want to take a couple of quick moments. What are we talking about with respect to perfect squares? Something times itself, the exact same something. So if we're talking about perfect squares, well, first thing, variable-wise, x squared, y squared, those are clearly perfect squares. But numerically speaking, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, 10 squared is 100. Our book and the authors of our book, they basically assume we know 1 through 10 squared. So that when you see numbers like this screams out, hey, 64, well, that's really 8 squared. 36, that's really 6 squared, and so on. So it still maintains that form, even though we're dealing with numbers and not variables. The last thing to point out here, before we really get to work using this formula, it doesn't just have, when we talk about variables, it doesn't just have to be a simple x squared or y squared. If I had something like x to the 4th, I can notice through my rules of exponents, that's really x squared squared. Or x to the 6th is x cubed squared. Or x to the 10th is x to the 5th squared. What they want us to realize is any variable to an even power is x to half that power squared. So that's something, we'll get a little more practice with that, and we'll see a lot of just the perfect x squared, but to realize that these can be broken down as well and can also fit as a part of this formula. So now I'm going to jump right in. My directions are going to be to factor. And I'm going to start with number 1, x squared minus 64. And in this first one, I'm going to be so super literal every step of the way. For some people, this is such a friendly factoring technique that they could just jump in and do it. But for others, they want to be very clear and using a formula. So that I look at this one, again, we are going to see factor completely. So yes, 2 terms, but no GCF. That's the big deal. So what else do I look for? Well, again, 2 terms. Is it one of my special forms? You've only seen one special form so far, and it works perfectly. That is the perfect square. Minus 64. Well, 64 is 8 squared. So A is x in this problem. B would be 8. A squared minus b squared. Well, if this is x squared minus 8 squared, x is serving the role of A, 8 is serving the role of B. So when I factor it, the formula says A minus B, well, that becomes x minus 8 when I plug in, times A plus B, well, that becomes x plus 8 when I plug it in. And I'm done. There's my factorization. But now, number 2, we're going to do a bunch here. But number 2, we need to point out something very, very important. The reason this is called the difference of squares, difference is our math word for subtract. It needs to have subtraction. What I have right here, this is what we would call the sum of squares. I've got the perfect x squared here. I've got the 64, which we just saw a moment ago. That is 8 squared. So a lot of people have this temptation. If the difference of squares factors this way, won't the sum of squares factor as x plus 8 times x plus 8? And let's realize it's not true, folks. If I thought, I mean, again, it's a reasonable thought, but if I FOIL this out to check my work, well, x times x is x squared. X times 8 is 8x. Then these two, 8 times x is another 8x. 8 times 8 is 64. What we saw up here, if you've got a difference, you get the opposite signs here, and that eventually leads to this middle term canceling. But if you tried to do them as the same side, that doesn't cancel. It combines to a plus 16x. So this is not the factorization of this. This is the factorization of this. So it's incorrect. Now, I mean, it is the factorization of this, but for this part, that is not the correct answer. So our book makes this special note, and we want to make it here. A squared plus b squared does not factor. That's just one example, but I could do this generically. There is no way that I would be able to have these 2 binomials have a plus term here and not end up with a middle term in between. So this one is just can't factor. It's done. Now, I don't want to trick you. As far as our problems, if we're being told to factor, something will factor, but just wanted to bring that up here. That is not the same thing as that. This cannot be factored. So let's get back to more of our real problems. Let's go to number 3. And for number 3, let's look at 4x squared minus 25y squared. This is a perfect example of this. In this one, well, it's not just an x squared. I've got a 4. But I know a 4 is one of my perfect squares. It's 2 squared. The y is a perfect square. That's great. And I also know 25 is a perfect square. So what we're trying to point out in this problem, you're not just limited to a and b just being a number or just being a variable. Here, a has both number and variable component, but break them down. 2 squared has a base of 2. X squared has the base of x. So a would be 2x. And similarly here, b, well, this needs to be b squared. So plane b would be the 5 and would be the y. So my a, my b, I follow my formula. This would factor as 2x minus 5y, a minus b, times 2x plus 5y, a plus b. All right, let's move along to number 4. Number 4, let's look at x to the 10th minus 100. All right, not obvious right off the bat, but I see a binomial. I'm being told to factor. Well, it's got the minus in between. Let's see, 100 is 10 squared. Well, that kind of gives me a hint to think, what about perfect squares? To then realize, oh yeah, that's where I could break that exponent apart. X to the 10th is x to the 5th squared, right? 5 times 2 would get me to the 10, so I could make that separation. So therefore, a would be x to the 5th, b would just be plain 10. And again, remember everybody, some people on the basic examples, they don't have to write this stuff out. They just fill in their formula. But then for the harder examples, they're trying to follow their formula, but they goof. They don't copy what is a, they copy what is a squared. They go, okay, well, a squared is x to the 10th, b squared is the 100, but that doesn't help me when I move to here. So that's where you got to break it down. That's why you look at this. Well, that's the a, and there's the square, hence a is just the x to the 5th. That's the b, and there's the square, hence b is just 10. It's not b is 100, it's just b is 10. But once I recognize that, very nice, a minus b, a plus b. And I'm finished. And one more like this, number 5. What if I had x squared y squared minus 36? Well, back in number 3, we realized that a and b don't just have to be just a number or just a variable. They could can contain aspects of both. Well, now in number 5, it could have multiple variables. I see perfect squares, I see perfect squares. I look at 36, that is 6 squared. Well, if both of these are squared, both of these need to combine to be a squared, so a will contain both rudimentary pieces. Just like we went back here, 2 squared x squared, a was 2x, 5 squared y squared, b was 5y. Well, in that same way, if a squared is x squared y squared, a would just be the plain xy, b would just be the plain 6, a minus b times a plus b. All right. And now as we move along, my next couple of examples, we're still factoring, but now I'm just changing that to factor completely. Because we get reminded one more time, anytime we learn a technique, that technique is never isolated by itself. That technique always can be combined with other techniques. We always have the possibility of multi-step factoring. So let's have this as number 6, factor completely. X to the 4th power minus 81. Well, okay, first things first, I'm looking for GCF. I don't see anything. Doesn't seem too troubling here. The 81, well, okay, that's a 9 squared. Makes me feel good about the squares formula. I got the minus in between. X to the 4th can be treated as x squared squared. So a will be x squared. b will be 9. So as it factors, a minus b times a plus b. And we feel good about this, but this is where every time we factor, we never just walk away. We always just say, can I do more? And you go back up to previous problems that we've done. Can I do more? Nope. No GCF, no nice special forms. There's no trinomials. Those answers were as good as they were going to be. But you come here and you realize, wait, that can still keep going. X squared, still a perfect square. 9 is 3 squared. So now I can keep going. And it's more difference of squares. Reset, I've already used a and b, that's done. Now in this case, a is x, b would be 3. So this will factor a minus b times a plus b. And what about this? Well, tempting, everybody. I see a perfect square, 9, that's 3 squared, another perfect square. But this is that sum of squares we talked about. That one is stuck. We're done. This factors, this kept going, but this was stuck. That is the final answer to number 6. Let's keep going. Number 7. Now let's look at 3x cubed minus 75x. Not x squared, just x. Sorry about that. Just an x. Well, I see a binomial, and if you're just so locked into what we're doing, you're thinking about what's a and what's b because you already see the minus. But these are not perfect squares. X cubed, nothing fancy that you can do like we did here. That doesn't work. 3 is not a perfect square. 75 is not a perfect square. It just feels like I'm stuck. But then I remember, no. First things first, is there a GCF? Is there a greatest common factor? And there is a greatest common factor here. 3 and 75 have a common 3. X cubed and x have a common x. 3x comes out. X squared left here. 3x comes out. Minus 25 is left here. So I feel good. I got my GCF, but I don't walk away. I look here and say, can I keep going? And yes, I can. I see a perfect square here, and then I'm looking at 25. Well, that's 5 squared. A is x, b is 5. And this is what I mean, folks. I'm really being repetitive writing this out. Some of you, maybe in the harder cases, you want to write out specifically your a and your b. But in these nice simpler cases, you just run with it. The 3x comes along. X squared minus 25. X minus 5 times x plus 5. And now I'm definitely done. Linear factors like this, linear, again, variable to the first power, unless they have a common number, there's no other special forms for stuff like that. So a nice job on number 7, and we'll finish up with this first special form with number 8. Number 8, we're looking at x to the 4th minus 10x squared plus 9. And for number 8, we start off by saying, well, I don't know. I don't see any GCF. This is a trinomial, so it definitely is not a difference of squares. Difference of squares is a binomial. But that's where go back to section 10 and realize this is still a nice trinomial. This exponent, half that exponent, no power of x. So when it factors, instead of being an x and an x, it'll be an x squared and an x squared. But I still need all my trinomial stuff. I need my grouping number. 1 times plus 9 is plus 9. The factors of 9 that add to 10 are 1 and 9. But they need to add to negative 10. So So it's really a -1 and a -9. Let me go through the whole process. Break up the middle. X to the 4th stays. -1x squared minus 9x squared plus 9. First grouping, second grouping. First grouping, x squared comes out. X squared left, -1 left. Over here, 9 as my GCF. Take the minus with it. X squared left here, -1 left here. X squared minus 1, common factor comes out. X squared minus 9, what's left behind? So it was a little bit of a harder trinomial, but here's the real big thing, everybody. What's left? That and that, both of them are difference of squares. So up here we saw after we did some factoring, here it was starting off as a difference of square, but after the fact, we still ended up with a difference of squares that could keep going. This one was done. This one, they're both perfect difference of squares. Over here, the second one, a lot of people see that one easier. X squared is obvious, 9 is 3 squared. It's easy to miss it here. You see the perfect square, but it's easy to miss 1 and forget that no, 1 is really 1 squared. So the first one, a is x, b is 1, x minus 1 times x plus 1. The second one, a is x, b is 3, so I'm getting x minus 3 times x plus 3. Okay. This one, again, we did our difference of squares, and in part 2, we'll move into the other special forms.